Hi everyone, so we're going to look at the determination of iron in cereal lab. Okay, now interestingly, when we do this in class, it's actually quite a complex experiment experimentally. That's the bad news, but the good news is obviously we can't do the experiments. You guys, we're going to give you the data, which is kind of hard to get in class, so kind of the hard work, if you like, has been done for you. Okay, you're just going to use the data to answer the questions. All right, so if you download the lab from, the Canvas site, you'll find out lots of stuff about the experiment, okay? But when we get into the nuts and bolts, I'm actually going to send you, and this is just one of the 12 sheets, okay? So there's your data sheet from your lab. Throw that away. Okay, I'm going to send you via email, obviously, different data sets for different people. I'm going to go through laying this 12, I'm going to go through number 12. No one's going to get number 12, I'm just going to show you number 12, right? So I'll show you how we actually get this information and then actually how we use it, all right? Now we'll put that on the back burner for a second because I want to give you kind of my standard pre-lab, okay? So when I teach this in the regular semester, we all come to lab, we have 20 minutes kind of discussion about the experiment, kind of show you what to do and how to get the data. Okay, so I'll do that right now. So what we're doing is determination of iron in cereal. Okay, so we get some, usually we get in lab total, right? And total is kind of an interesting cereal because it's called total for a reason, right? It contains 100% of your recommended daily amount of a bunch of vitamins and minerals, iron being one of them, okay? So total contains 100% of your RDA, recommended daily amount, or RDV, recommended daily value, okay? So what we're going to do, we're essentially going to find how much iron is in the cereal, okay, and then say, is the label lying to us or is it true? Okay, is it really 100%, right? So we're going to learn about the method of, make sure I get this right, absorb like a sponge, right? Absorption spectroscopy, all right? And then determine the amount of Fe, iron, in a cereal sample. It's actually Fe2+. Okay, we're able to dissolve those ions, which we need for our experiment, but fundamentally when it's in the cereal, it's in the solid form. We'll extract it as a dissolved iron. Okay, now a bit of background, right? So absorption spectroscopy. It's a real simple concept, yeah. So some metal ions, other things, complexes, molecules, some of these things absorb light of certain color, right? Okay, so say an iron 2+ ion absorbs blue light, right? The more ions are in the way of the light, the more it absorbs, so the more intense the color, right? Okay, so it's a simple observation. The deeper the color, the more ions in the way. Okay, and that's called essentially Beer's law. All right, so we can relate absorption, which is really how many ions are in the way, to how much light's absorbed. All right, so let's do a little picture here. So transition metal complexes. We're going to make an iron 2 solution, which is called a complex. Absorb light at specific wavelengths, right? So that's the symbol for wavelength. Visible light runs from around 700 nanometers, which is red, to around 450 or something, which is ultraviolet, right? So infrared is past 700, ultraviolet is past 450, and in that range there is visible. Okay, so we see in that range, and it's red, orange, yellow, green, indigo, violet. Sorry, blue, violet. Okay, all right. So those are the colors in the visible spectrum between about 650, 700, and about 450 nanometers. Okay. The shorter wavelength is the ultraviolet or violet end, the long wavelength is the red moving into infrared. Okay, now if I get a cuvette, and hopefully I'll show you a picture of a cuvette, right? We get these little cuvettes, which are these little, if they're nice ones, they're made of quartz, right, but plastic in our lab, right? So they're about this big, right, okay? And we fill it with our solution, and then we shine a white light. So white light has all the colors of the rainbow, right? And if I have some Fe2+ in here, all right, so this light goes in, and what the Fe2+ does, it absorbs in the kind of the green, it absorbs kind of in the green area, right? So what comes through is some red light, some orange, and a little bit of blue down here, okay? And that's what's seen. That's called the complementary color. So it absorbs green and you see what's left, which is kind of a reddish brown, okay? So you see the complementary color. Red, brown. Okay, so that's the kind of the color of rusty water, right? So reddy brown color. That's because the white light that comes from the sun hits the rust essentially, it absorbs the green light and you see what's left, the complementary color, right? Okay, so therefore absorbs green. Now the color we see is green, which is approximately 508, sorry, the color that's absorbed is green, approximately 508 nanometers. Okay, so if you like, one photon of green light is absorbed for every one ion in the way. That's a simple way to think about it. It's not necessarily true, but it is proportional. Okay, so the more green light absorbed, the more iron 2+ in the way, because it absorbs at 508, which is green light. Okay, now we put that into a law, right? Absorption, that's the fraction of light absorbed at a specific wavelength, right? 508 in this case. All right. So if I have absorption of 0, it's a window. All the light goes through, right? If I have an absorption of 1, it's a brick wall. No light goes through. So from 0 to 1 is the fraction, yeah. So 1 is absolutely everything's absorbed. 0 is nothing absorbed. Should we do our experiment, we get deionized water and calibrate for 0, we'd find, hey, this is what 0 looks like in terms of, you know, all the light going through, right? Okay, so 0 absorption, 100% transmittance, so that'll be deionized water, okay? And if you want to read the procedure, you can, right? If you want to go to the group site, all right? So absorption is proportional to concentration of Fe2+. Proportional, right? So they rise together. The more stuff in the way, the more color is absorbed, right? Okay, that's all you need to know. The actual law to make it equivalent is what's called the extinction coefficient, the exchange rate between kind of absorption and concentration. The concentration itself and the path length, right? But that's a constant and that's a constant, so absorption is proportional to concentration. And we need that to draw a graph, right? So if we think about a graph, what we're going to get, our graph will look like this. If I do a graph of absorption versus concentration of iron, right, there will be an intersect at 0, 0. No iron, no absorption, right? And then we'll get a linear relationship. We get a linear relationship, and that just follows through like that. All right. Now, in your lab, what you would do is you'd actually make these various solutions, okay, and you'd record their absorption for known concentrations. So you get these points on the graph, so you know the concentration because you made that solution, you'd recorded the absorption, right? You know that concentration, recorded the absorption, and you get a straight line. Okay, now that works for every iron solution, yeah? Okay, so that's like your standard plot. Okay, fair enough. Now, let's just go to the next page real quick. When we actually look at our data for this experiment, okay, they amazingly don't give you that information, all right? So you'd record this and then you'd plot it, right? Okay, so you make these concentrations and then you plot them. So where are they? Well, honestly, it doesn't matter, because at the end of the day, they use that information to plot the graph, okay? So there's the graph. This is absorption, and this is concentration in milligrams per 100 milliliters, right? That's our unit we're going to use, right? Okay. Now, if you think about it, when you put your sample in there, so you make your serial sample, you put it in, right? Okay, it's going to have an absorption. Maybe it's exactly 0.5. It won't be, right? Pretend, right? So if the absorption is here, we just read across till it hits there, and then we read down, and we can find out the concentration of iron in there. Fair enough, right? But if you think about it, we don't have to actually use the graph manually, because the computer, unlike the Death Star, can hit it, right? So here, this is the equation of the line. Should we use the LabQuest software, this just pops out, right? This just pops out, yeah? So y equals 1.0794x plus the intercept. The intercept's tiny, right? So it's not perfect, it's actual lab data, so it should be 0, 0. It's not quite, but that's okay. That's lab data, right? So if we think about it, y equals, now your graph may be different, right? So use the numbers from your data set, right? I'm going to send you the data sets by email. So the intercept is tiny, right? So y equals mx plus b, right? Now if you think about it, y, that's the absorption, right? That's this side, equals 1.0794x, x is concentration of iron, plus the intercept, that little distance there. Okay, what's your goal? Sorry, let's move it up. What's your goal? Your goal is to figure out the concentration of iron in your cereal from its absorption, right? So just skip straight to it. You don't need to do all the work up because you have the graph, right? So in class you would have worked a long time to get this graph, and I'll just show you like a real one. So you just spent a lot of time, groups of 4, working on this, and there's the equation of the line, right? So that's a really nice one, okay? So there it is, all right? So that's real experimental data from a student years ago, all right? Here's your, here's your practice data, right? So pretend you did the experiment, okay? So what you're going to do is you solve for Fe2+. So you'll get milligrams in 100 milliliters as an answer. Fantastic, okay? So rearrange there, okay? So that's your experiment in a nutshell. Now let's go back. All right, so let's just get your data set. Now if you have access to that email, I really recommend you print out the data and we'll go through mine and you can look at yours at the same time. So you can have a different group, right? I'm 12, you're gonna be 1, 2, 3, whatever, right? Okay, now the percent from iron in 1 serving. Now be careful here because I wrote down that number. All right, you could look it up, but it is actually, what's my number? I think it was, where is it? It's actually in the lab here, okay. 18 milligrams, okay. So RDA equals 18 milligrams. So what we got to find out, yes or no with a value, right? Is there 18 milligrams in 1 serving of total, right? Okay, so if we looked on the cereal packet label, and feel free to look up the label, right? You can find it online. If you look on the label, yes, it claims it has 100% of your daily iron, which is 18 milligrams, okay, in 30 grams of 1 serving is 30 grams. So it claims there's 18 milligrams in 30 grams of cereal, right? Let's look at your data set. What have you found? Well, you found you grind up your cereal, you don't use 30 grams, you use essentially 1 gram, right? So the amount you find by your experiment, you're actually going to multiply it up by, a conversion factor approximately 30 to get the true amount of iron in there, right? So you find out in your experiment how many milligrams of iron are in approximately 1 gram, right? Okay, and then you can multiply it through, okay? Now, these numbers here, these relate to your experiment, okay? So, I'll talk about the math as we go through, okay? So let's look at your data analysis, all right? So, first things first, a graph of absorption versus iron concentration is provided as a calibration curve. Use the calibration curve. What's the iron concentration for your sample? All right, so we just talked about that. Do this math here, okay, and find out how many milligrams are in your sample, all right? Okay, check. Okay, graph. Equation. Okay. Now, this is where you have kind of a slight experimental trick, right? So when we do your experiment, yeah, we don't, when we drain, if you like, the iron solution from the cereal, we get like a big old volume, right? Okay, so we actually recover in this experiment 85.5 milliliters. So we get this iron solution, so we drain like a tea bag, right, all the liquid out of our iron when we've digested it, and we get 85.5, right? So all the iron from that 1 gram is in that solution. But then we just nip out 10 milliliters to test, yeah? So obviously there's going to be less iron in the 10 milliliters than the 85 by a factor of 8.5 in this case, yeah? So we have to account for that, right? So that's why it says multiply the mass of iron, so by VT over 10, right? So in my experiment, VT was the volume I got from my experiment. So it's like I'm ratioing up to get the right number. So I didn't actually get the number I got from here. I got that much times number 2, if you like, right? Okay, times number 2. Okay, so from that point forward, it's actually pretty easy, right? So let me just show you my data set, right? Actually, my math from oh, there we go. Here's one I go through in class, right? So you use your result from step 3, right? And the mass of your cereal sample to determine the amount of iron in 1 serving of cereal. Show calculations. What does that mean? So the result from 3, right? That's here, all right? How do you think you do that? Let's think about it, right? So use your result from step 3. This is iron in sample, okay? And the mass of your cereal sample to determine the amount in 1 serving, all right? So you have here, if I go back, let's just look at it. Oh, where is it? Too many pieces of paper, okay. Excuse my flopping around, okay. So here, 0.976 grams, so you're going to make a conversion factor, 0.976 grams. Your number may be different, all right? Cereal equals the value you got here, X milligrams of iron, right? And then it's just a conversion. If I want the amount in 1 serving, I need it in 30 grams. So 30 grams times 0.976 grams, okay, equals. And obviously it should be around 18, right? Because that's what the book says, that's what the label says, okay? So let's just recap. Rearrange the equation on the graph to solve for Fe concentration, right? Okay. Don't worry about the 100 milliliters, just go with the milligrams, right? So we figure out how many milligrams are in that 10 milliliter sample, right? And because you didn't collect 10, you collected 85, you just ratio that up, and that gives you the milligrams of iron, okay? That's, you know, number 2, right? Previous page. That's the milligram of iron in your sample, which was approximately 1 gram, all right? So in your approximately 1 gram, you had that many milligrams, okay? So I'm bringing that number down there, okay? Use a conversion to find out how many's in 1 serving. And then you can just do a percent, right? So it says, you know, actually this one's number 5 is actually easy, right? It's just use the daily value for the percent iron in your cereal box to determine the theoretical mass of iron, okay? So it's, you know, it's obviously just 18 milligrams, right? That's the claim from the box. So you can just write that, right? Okay. Then how does your theoretical, so maybe you got 17 up here, right? So how does it compare, right? So if you do a comparison, it's A minus B over B times 100. Oh, times 100 for a percent, yeah. So it's the difference between yours and 18. So say you got 17 here, right? divided by the real thing, divided by 18, right, times 100, and that'll give you a percent error. I don't want to know how right you are. I don't want 17 over 18 times 100, right, because that's like, 99% right. I want to know how wrong you are, so it's the difference. Okay. Possible sources of error, well, my advice is common sense, read the procedure and things will pop out. Okay, so hopefully that makes sense. Okay, hopefully that makes sense. If you have any questions, again, discussion and office hour. Okay, but just let's go through one more time real quick. Okay, you collect around 1 gram of ground up cereal from the total, right? The cereal box, right? You digest that and you can read the procedure to turn the iron in the 1 gram approximately, and don't use 1 gram, use the actual number, right? So that iron is leached out, it comes out into solution, yeah? And you drain that solution and you measure its volume, yeah? You then take, so all the iron from the cereals, the 1 gram is in this, right? Then you take 10 milliliters of this, yeah? You take 10 milliliters of this and take it away for analysis, yeah? Okay, so you throw that in your machine and using the equation, you see what the concentration is, and just think about milligrams. Just work out, don't worry about that. That's kind of a reference, right? You work out how many milligrams are in that 10, yeah? Fair enough. And that's what you get here at the bottom, right? Okay. Then flip over. Well, actually, that 10 was taken out of a bigger volume, right? So there's actually that ratio bigger amount, right? So the number I got from the previous question times that ratio, right? Now your number will be different, right? It might be 90 or something, right? Whatever it is. And that gives you the real amount of iron in the whole 1 gram, right? And you can rate yourself a conversion factor. However many grams of cereal I had equals that milligrams of iron. And to figure out the amount from your experiment in a serving, which is 30 grams, just use that as a conversion factor. Boom, okay? We know how much is in 1 from the label. I give you that information. Work out a percent error or a percent difference. How good, right? How good? All right, is the box lying to you, yes or no? Okay, so if this data is good, you should be pretty close to 18 here, and this should be a pretty small number for an error. Okay, all right. So I'll grade them based on, I'm not sure, to be honest. I didn't work out the math for every single sample. Okay, so what you're going to get, you'll get from me an email via Canvas with your data set, right? A bit like the mixtures, right? Okay, and then my advice is, just use that data set because it's basically just the data sheet for the experiment with gaps, right? So I filled in number 12, so just fill in, say, get number 3 or something. Fill in number 3, so you can do the math here for the graph, work this math through, save it, send it as a single PDF or Word, PDF probably better, and you're good. Okay. Hopefully that makes sense. Okay, I'll get this posted, and today is, you guys like, are you losing track of days? Allegedly it's Wednesday, right? So I'm going to give you plenty of time for this one because, it's a concept thing, all right? And, we worked pretty hard this week. There's a lot of concepts there we did with the balancing and things like that. So I'm going to make this due on Monday, all right? So like Monday of next week, I'll, no rush, right? So work on it over the weekend. I would say prioritize the lecture material. Okay, it's very, very important you know how to balance an equation. Very important, right? Okay, and if you watch the video, remember there's a 2-step process. Don't fall into the trap we talked about. Okay, all right, stop there. And any questions, discussion, and today's Wednesday, so tomorrow, if you've seen this immediately, tomorrow at 9 is the office hour. Okay, all right, stop there.